Okay, today we started into a more detailed discussion of hydrostatic fluids, specifically how pressure varies within them. That'll be the building block for how forces manifest themselves in fluids and how hydrostatic fluids create forces on structures or walls or even other interfaces. Today our analysis focused on defining how pressure varies as a function of x, y, and z, where x and y are the horizontal dimensions and z is the vertical. So to be clear here, I'm saying z is the vertical dimension. So we have z positive upwards. All right, the first key result, we used a little control volume to define this, is that dp dx and dp dy are both 0. In the vertical dimension, though, because of the weight of the fluid acting downwards, the pressure increases with depth, so that dp dz is equal to minus gamma. Now, I didn't really talk about this, but that minus sign is what forces the pressure to increase as depth decreases, or as you move downwards. So pressure increases as z decreases. So as you move down through a fluid, pressure increases under the action of the weight above. Now, so that's the first basic result. If the density is equal to a constant, remember, just recall that gamma is equal to density times gravity. If density is equal to a constant, then we can say, we can integrate the expression given here that I'll circle in red. We can integrate that expression to say that p over gamma plus z is equal to a constant. Or, connecting 2 points, we can say p1 over gamma plus z1 is equal to p2 over gamma plus z2. As I noted near the end of lecture today, it's important to keep track of what fluid this gamma is. This is the fluid between points 1 and 2. So between 1 and 2. So as you move from point 1 to point 2, you use the characteristics of the fluid between the two to define this piezometric head. This then allows you to solve for P1 as a function of P2 or Z1 versus Z2 or any other combination of these factors.